Hi everyone, this is Dr. GVR Seshagiri Rao, Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. So we are discussing about solid mechanics and material subject. So in this subject, in previous sessions already we have discussed about simple stresses and strains and what is the definition of stress and strain, what is the relation between the stress and strain, and the different types of stresses and strain equation and different elastic constants we have studied. So today, I want to discuss about stresses due to gradual, sudden and falling load. So whenever the component subjected to gradual load or sudden load or falling load. So how do you calculate the stresses? We have seen in previous sessions uh, how to calculate the stresses due to normal loads and then stresses in the composite bars. So how do you calculate stresses due to temperatures? We have seen. So in this, we will see the stresses due to gradual loads and sudden and impact loads. So before going to enter this topic, we will see the course outcome. So at the end of the course, the students should be able to answer, explain the concepts of stress strain, material constitutional relationships, and then strain energy induced in linear, elastic, homogeneous, and isotropic materials subject to forces. Now, already have seen the concepts and relationship. But in this session, we will see the strain energy and the stresses due to the different loads. See, today's topic is stresses due to gradual, sudden, and falling load. Strain energy due to gradual applied load. So, to calculate when the body is subjected to gradual loads. So, let us consider a body which is subjected with tensile load, which is increasing gradually up to its elastic limit. You know, in stress strain diagram, elastic limit we have seen. In this limit, there is a relationship with the stress and strain. The stress is directly proportional to strain. Here, whenever the load is increasing gradually up to elastic limit only from 0 to value P. So as shown in the figure here, the extension diagram shown here, the 0 to here starting O origin to value P. So load versus extension. And therefore, deformation or extension of the body is also increasing from 0 to x. The deformation also increasing from 0 to x. If load increases, then the automatically deformation also increases. So similar up to the load up to P and then the deformation also up to x will be happen. So in this diagram, the load extension diagram displayed here. So this is up to elastic limit zone. So the clear diagram shown here, the load versus extension. So in this, load directly proportional to extension. Extension, that is deformation. P directly proportional to X. So let us assume the sigma is the stress developed in the body. A is the Young's modulus of elasticity of the material of the body. A is cross-sectional area of the body. P is here gradually applied load, which is increasing gradually up to its elastic limit from 0 to value P, as we have discussed in a previous slide, up to elastic limit. So now calculate load is equal to stress multiplied with area. Already you know the stress is equal to load per area. In starting introduction session, we have seen all these equations, formulas. So here X is equal to deformation or extension of the body, which is also increasing from 0 to X. Deformation or extension also increasing 0 to X. If load increases, this deformation also increases. So take L is equal to length of the body. Now the volume of the body is L multiplied with the area. Now you can calculate strain energy U stored in the body. How much energy is stored in the body? That is called as internal strain energy. So now when a body will be loaded within its elastic limit, the work done by the load in deforming the body will be equal to the strain energy stored in the body. So nothing but the strain energy stored in the body is equal to work done by the load in deforming the body. So how much work done by the load in deforming the body? So here, see, the body is subjected to gradual load. If load increases, the extension also increases. So some deformation occurred in this body. So 0 to X. So how much work done by the body to deform the body from 0 to X? That is called as strain energy in the body. So here the strain energy stored in the body is equal to work done by the load in deforming the body. So now you can write the strain energy stored in the body is equal to area of the body, area of the load, extension curve. The area of the load extension curve That is the area of the triangle ABC. The stored in the body means the area of the triangle ABC. Here you can see in this diagram. So what is the area of ABC? ABC. So area of the triangle, half into base multiply with height. So here you can write in this triangle ABC. In this is base AB and height. Now the strain energy is equal to half multiply with AB, that is base, and BC, that is a H. But in this diagram, we have applied load. See, once again A, B, C, from here up to X, and here the point is P. The point is P. So 0 to P, the load. So therefore, this value is P. The AB is X, 0 to X. So AB is equal to 0 to X and BC is equal to 0 to P value. So the maximum reached deformation is X. The maximum load is P. So therefore, the strain energy is equal to half multiply with AB, that is X, and then BC, P value. So let us use the value of P is equal to sigma into A. The stress is equal to load per area. So that P is equal to sigma into A. Now substitute this P value in above strain energy equation, which is determined above, that is U is equal to half multiply with the sigma into A. As X is equal to sigma multiply with L by E. So this is why this sigma X is equal to sigma into L by E. So write again U is equal to half multiply with X into P. So here P, in place of P, you can write sigma into area. But X is equal to, what is X? Deformation. So deformation, actually the stress is, as per stress strain diagram, stress is directly proportional to strain. So you can write in terms of elastic modulus of elasticity E multiply with strain. Strain is equal to sigma by E. So what do you mean by strain? The strain is change in length by original length. So deformation is X and change in length is X and original length is L, is equal to sigma by E. So delta L is equal to sigma by E multiplied with L. So what is this delta L? The delta L is change in length, that is deformation, X. So you can write X is equal to sigma multiplied with L by E. So that written like this. Okay. So now, therefore, the strain energy stored in a body when load will be applied gradually will be given by following equation. What is that equation? Sigma square by, that is U is equal to sigma square by 2E into volume. So what is this? So now substitute the X sigma L by E. So actually U is equal to half multiply with X multiply with P. P is equal to sigma into E. A. But X is equal to delta L, that is sigma by E into L. Now substitute this above equation, you will get the sigma square by 2E into B. So U is equal to half multiply sigma by E into L multiply sigma into L. So this is sigma square by 2E into L into A. What is this L into A? Length multiplied with area is nothing but volume. So volume is equal to L into A. So that you can write the strain energy. Strain energy is equal to sigma square by 2E multiplied with volume. Whenever the load will be applied gradually. So in this case, the strain energy is equal to sigma square by 2E into V. So next second case, strain energy due to suddenly applied load. First one we have seen gradually applied load. Second we are discussing this, we will see the suddenly applied load. Then we will discuss with impact load, the sudden fallen load. Sudden and this falling load. Let us see the load extension diagram as displayed here for this case, where body will be subjected to sudden load. And we will find out here the stress induced in the body due to sudden applied load, and simultaneously we will also secure the expression for strain energy for this situation. So load extension diagram as displayed here. For this case, the body will be subjected to sudden load. So, and we will find out the stress induced in the body due to sudden applied load. See here, the extension diagram shown here, 0 to X extension and 0 to P, there is load diagram. In previous case, we have seen gradually applied load, but in this case, not like that, suddenly applied. So 0 to P, so suddenly applied, the extension will occur, deformation 0 to X. In this, assume the sigma is equal to stress developed in the body due to suddenly applied load, and the E is Young's modulus of elasticity of the material of the body. A is cross-sectional area of the body. P is sudden applied load which will be constant throughout the deformation process of the body. One is sigma, another one is E, Young's modulus of elasticity of the material of the body, and A is cross-sectional area of the body. P is sudden applied load, so which will be constant throughout the deformation process of the body. The strain energy due to suddenly applied load. How do you calculate U? So deformation or extension of the body X, same, length of the body L, and volume of the body is length multiplied with area, strain energy stored in the body. So in this, the area of the body means area of this extension curve. So this is an extension deformed body diagram. So what is the area? So your area you can calculate 0 to P, that is P multiply with and deformation, height and this the length, increased deformation, that is X. It gives area of the body. So that the strain energy stored in the body is equal to work done by the load in deforming the body. So strain energy stored in the body is equal to area of the load extension curve. The strain energy stored in the body is, now you can write U is equal to P into X. So again P you can write in terms of sigma into E. X also you can write in terms of sigma and modulus of elasticity. So as you know that the maximum strain energy stored in the body U will be provided by the following expression. So as mentioned already here, so I will show you. U is equal to sigma square by 2E into V. So already you know U is equal to in previous case, the strain energy stored in the body when load applied gradually will be the given sigma square by 2E into V. Here mentioned the U will be provided by the following expression. U is equal to sigma square by 2 into V. But here the volume is equal to A into L. So but volume U is equal to P into X. The strain energy stored is equal to work done by the body. So that is area of the load extension curve. This is equal to strain energy stored in the body. So now equate the strain energy stored in the body is equal to sigma square by 2 into A. So now you can write in terms of X, that is in deformation, P multiply with in X place sigma by E into L, that is deformation, is equal to sigma square by 2E into AL. Already you know this equation written. So now calculate the P value. So sigma by sigma get cancelled here and LL get cancelled. So you will get sigma A by 2. So now you can write the stress is equal to 2P by A. So therefore, we can say here that the maximum stress induced in the body due to the sudden applied load will be twice the stress induced in the body with same value of load applied gradually. Sigma is equal to 2P by A. But in case of gradual load, the stress is equal to load upon area. So it means you can say the sigma is equal to the maximum stress induced in the body due to sudden applied load will be twice the stress induced in the body with same value of load applied gradually. Whenever you applied load is same. So next last condition. So we have seen gradual and sudden, and now we'll see the falling load, that is the impact applied load. So let us see the following figure. In this, the vertical bar supported a load with height h. The length of the bar is L, and whenever the release of this load suddenly, the impact. So what is the impact of this load on this surface body? That is deformation. So how much deformed? See that the following figure where we can see one vertical bar which is fixed at the upper end, fixed, and lower end there is a collar at the lower end of the bar, the collar is there. Let us think that one load is being dropped over the collar of the vertical bar from a height h as displayed in the following figure. So whenever the load released on this collar, clear. So what is the impact of this load? See, let us go ahead step by step for easy understanding. However, if there is any issue, we can discuss it in comment box which is provided below this post. Means whenever we are discussing in online session, so we can take these comments. So we have the following information from above figure where a body is subjected to with an impact load. So strain energy is due to impact applied load. So here given why this step is given here. So if you have any problem, you can give comment in our YouTube link. So stress developed in the body due to impact load. Young's modulus of elasticity of the material body E, and A is the cross-sectional area of the body, and P is the impact load, and X is deformation or extension of the body, that is vertical bar. So let us assume sigma, E, X Young's modulus, and A also but here difference is, in first case P is the sudden gradual load, second case suddenly applied load, and third one is impact load. And X is same, deformation or extension of the body whenever released this load. So length, L is the length of the body, that is a vertical bar. V is the volume of the body, that is vertical bar L into A. V is equal to U is strain energy stored in the body, that is in vertical bar. So now, the strain energy stored in the body, vertical bar, is work done by the load in deforming the vertical bar. So how much work done? Strain energy stored in the vertical bar is nothing but load multiplied with displacement. strain energy stored in the vertical bar is equal to, what is the load? The load is P and the displacement is H plus X. So how much displaced? See in this diagram. So this X deformed plus H, the height of the load. So total deformation is equal to H plus X. This is delta L. So now in this strain energy calculation, the strain energy stored in the vertical bar is equal to load multiplied with the displacement, the total displacement. Load already you know, this is impact load. And H plus X is the displacement. Now substitute in strain energy equation. You know the strain energy stored in the body U will be provided by the following expression. You know this equation U is equal to sigma square by 2E into V. V also you know this is A into L. Now equate the strain energy stored in the body due to impact load, that is P into H plus X. So P into H plus X is equal to sigma square by 2E multiply with AL. Now the strain energy is equal to P into H plus X equate to this equation. So as we know, the strain energy in the body provided with the following expression, that is, let us the value of extension or deformation in the above equation will have this X value deformation. So much deformed. The deformation is X delta L. So here the P into H plus sigma L by L. Why? Because you know the deformation X is equal to sigma E by E into L. So substitute here sigma L by E in place of X. So that is P into H plus X is equal to sigma square by E into AL. So in equation sigma square by 2E into AL. P into H plus X. H plus X is equal to half sigma square by E into volume. So here simplify this equation. P into H plus P into sigma L by E into sigma square by 2E into AL. Now simplify this equation. Sigma square by 2E minus P sigma by AE plus PH by AL. So here, so simplify AL minus P sigma L by E is equal to PH. So here take common LCM, or otherwise AL sigma square by 2E So or otherwise divide with AL. So here AL, AL and AL. So here what will happen here? Sigma square by 2AL, AL get cancelled. Here LL get cancelled. Sigma square by 2E minus P sigma by AE is equal to PH by AL. So now take sigma square minus 2, take LCM here, and 2P sigma by A into 2PHE by AL will get. So after that, simplify this equation, write down the sigma square terms the left side, LHS and RHS. And you can write this equation in terms of A minus B whole square. A square plus B square minus 2AB. So in the form of A minus B. And the P square by A square plus 2PHE by AL. So now take the value sigma minus P by A is equal to square root of P square plus B square by A square plus 2PHE by AL. So finally we'll get the sigma value is equal to P by A plus square root of P square by A square plus 2PHE by AL. This is the stress value when the body is subjected to impact applied load. Here sigma is the stress. So already we have assumed the stress developed in the body, and E is the Young's modulus of the elasticity, and A is the cross-sectional area of the body, and P is impact load, and deformation X. So here finally we will get P by A plus P square by A square plus 2PHE by AL. So here P by A is the stress induced when the body is subjected to gradual applied load, you know. In sudden applied load, 2P by A, the sudden applied load stress. And then here added the extra term is H. So that is height of the body. Why? Because the body is, the load is released from with height H, that is impact. So due to this impact load, how much the body deformed, that is the X. The total deformation H plus X we have taken here. So that the strain energy need to calculate like this. So in this section we have learned the strain energy. What we have covered here in this session, we have discussed about strain energy due to gradual load, and then so in this we have taken area of the extension curve. So finally we have equation U is equal to sigma square by 2E into B. Similarly the sudden applied load, we have proven this 2 times of the gradual applied load, 2P by A. This is the final equation. And suddenly applied load we have seen. After that we have seen impact applied load. So due to impact load information the already given in the figure I have discussed. So in this, we have calculated stress. So in this session, we have learned how to calculate the stresses when the body is subjected to different types of loads. In previous sessions, we have seen normal load. A uniform body is subjected to normal load, the tensile load or compressive or shear load. How to calculate the stress by using empirical relations we have seen. In this, we have calculated gradual and sudden loads and falling load. But in this, the energy, the whatever work done by the body to deform, that work done stored in a body as a strain energy. So that is concept of strain energy. The strain energy in the body is equal to the work done by the body to deformation. So that is nothing but the strain energy in the body is equal to the area of the body. Area of the body already you have seen this, the area of the load extension curve. Load extension curve. So finally the strain energy equation is the fundamental final equation is strain energy equation is equal to, say, U is equal to sigma square by 2E multiply with volume V. Clear? So the final equation is strain energy due to the impact applied load sigma is equal to P by A plus square root of P square by A square plus 2PHE by A. So these are the references I have taken for this PPT. S. Ramamurthy. The title of the book is Strength of Material. Publisher Dhanpati Rai. So R.K. Rajput, The Strength of Materials. You can take the publisher Chand publisher. So R.K. Bansal, the textbook of Strength of Material, title and Lakshmi Publications. R.S. Kurmi, Gupta and Strength of Materials. So latest editions also available. You can refer. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.